Hello, hello. This video will be going over Unit 5.1.2, How Can I Predict the Graph? Apologies for not being able to be there today, but we cannot push off Unit 5 any further, so we're actually going to go ahead and start the first unit here in video, and the next time I come in, we will go ahead and continue our lesson, going back to actually 5.1.1. 5.1.2 is a little bit more accessible using our video. So that's why we're starting out here. And we're going to not export the document going on there. And we're just going to jump right into our next unit and set the foundation for what we're going to learn for our next test. Let's go ahead and see. So naturally, we're going to start off with our objectives. So take a moment to write this down in your notes. In this section, students will investigate solutions of a function. It should be of a function. I suppose two works, but of is a little bit cleaner. Students will investigate solutions of a function and use them to sketch a graph that matches those solutions. I will know I'm successful when I can use the solutions of a polynomial to find its orientation, degree, and general shape. So please go ahead and write this highlight part in green in our objective. And as soon as we are done with that, we're good to continue. Please pause as we need to throughout this video to write what you need to do, to take notes, to catch up, and feel free to fast forward and rewind to catch whatever pieces of information that you may need to go over again. Okay, so let's look at our first slide, our intro into this section. So it's labeled Sketching Graphs, and it says, you can use a number line to represent the information about a given polynomial. And then I have two bullet points describing what's going on with my number line. Okay, so the first point says the bold parts of each number line, the bold parts of each number line below shows where the graph is above the x-axis. And the second bullet point says the open circles show the locations of the x-intercepts or roots of the function. Okay, so the first point is worded a touch weirdly, but it's essentially saying the bold parts of our number line represent where our graph is going to be above the x-axis. Remember, x-axis is going horizontally, meaning that anywhere that is bolded in black is going to be above the x-axis, and anything that is not in bold on the number line is going to be below the x-axis. And of course, the open circles are going to be the location where our line crosses over, or at least hits our x-axis. So it's going to hit it here and then hit it here. Specifically on our number line, we know that this is painting a picture of a certain polynomial. And it's saying, hey, this polynomial, this function, crosses through my x-axis at -5, 0, and 2. And what's happening is that there are certain areas where my line is above the x-axis. That can be here and also here, and everywhere else it's going to be below. So this is just giving us a setup, and we need to make sure we understand what each bullet point is saying, so we could use this information to then answer the question on the next slide. So familiarize yourself with what's being said here. As we go on to our next slide, we have the same information here. It says the bold parts of each number line below show where the graph is above the x-axis, and it circles the locations of the intercepts. And then it tells us to sketch a possible graph to fit each number line, then write a possible equation. It says each number line, we only have one number line. So for right now, we're just going to worry about this one right here. So take a moment, go ahead and pause the video, and see if you could sketch either on the whiteboard or on your notes a possible graph to fit this particular number line. And then we'll see about writing an equation. We'll maybe get to that part. Okay, we should have made an attempt on how to sketch this particular graph represented on this number line. Let's go ahead and explore what that is going to look like, okay? So let's first understand what the first bullet point is saying. It says the bold parts of each number line below show where the graph is above the x-axis. So the bold part is where my graph is above the x-axis. So right away, I'm going to go ahead and look. Okay, from -5 to 0 is one area where my line is above my x-axis. So I'm going to go ahead and just draw a line connecting -5 and 0. That is going to be above my x-axis. We'll call this my x-axis for lack of a better line right now. And then from 0 to 2 is also an area where my line is above the x-axis. And it says the open circles show the locations of the x-intercepts or roots of the function. So I know that my line is going to pass through -5, 0, and 2. And that's represented by my line actually touching those points on the x-axis. But this is not a complete graph. This is not telling me a complete story. And what is happening, though, is I need to infer information from my first bullet point. So the bold part of the number line is where my graph is above my x-axis, which means all the parts that are not bolded are where my number line is less than my x-axis. So that means from -5 into the left is going to be where my graph is lower than my x-axis. Similarly, 2 into the right is where my graph is going to be lower than my x-axis. So then I'm just working on my number line, but I'm using all this information to begin to sketch what a possible graph might look like. And as soon as I have all this information here, as soon as I'm able to discern what my x-intercepts are, what my behavior is around these particular x-intercepts, then I'm going to go ahead and take it to my coordinate plane. So as soon as you feel ready, you feel confident to tackle this particular kind of problem, then we're going to take it from just this number line, just our x-axis, and take it to our coordinate plane that has both our x-axis and y-axis. So we're going to be taking a lot of information from our x-axis, that being our x-intercepts. So first and foremost, I'm going to set my first x-intercept as -5. I'm going to set my second x-intercept at 0. And I'm going to set my third x-intercept at 2. -5, 0, and 2. So what this means is that I'm going to have 3 x-intercepts, 3 solutions, 3 roots for when my graph is equal, when my polynomial, when my function is equal to 0. And then I'm going to take my cues once again from what it tells me. So I know that to the left of -5, I'm going to start below my x-axis. So I'm going to go ahead and make my line. We'll make it red just to make it easier to see. To the left of -5, to the left of -5, I'm going to start below my x-axis. So I'm going up, going up, going up until I hit my -5. And from there, the information tells me that, okay, this bolded area tells me where my graph is above my x-axis. So I'm going to go ahead and continue that to the left of -5. I'm going up and going up, but I must come back down eventually because I have to come back to my x-intercept at 0. But then I get to go back up to the right of my 0. We're going to go back up until I hit my 2. And I never made that a specific point. So let's go and make that a point real quick. And then we're going to bring this back down because everything to the right of this point is going to be under my x-axis based on what it's... Oh, hold the phone. I would love to edit this out, but I just do not have the time for that. So let's actually go back and identify something. Let's see if I identified it up here. No, we did not. But this is the only place where my line is actually not bolded. So if you caught on that, you were saying, Mister, what are you doing? Good on you. But I missed that part because we're actually bolded to the right as well, which means we're actually going to go back up. To the right of 2, our line is going to be above the x-axis. That's what the bold part means. So that means that we're going to start at -5, go to 0, go to 2, and then we're going to bounce right back up, and we're going to go up above the x-axis after we go to the right of 2. And now we've taken our number line, what we had in the graph, and we change it into a sketch of what the graph of this polynomial might look like. As far as writing a possible equation, let me see what comes up. Yeah, let's go ahead and try and make a possible equation. So it doesn't mean we need to solve for the exact polynomial that we're thinking of. We're just going to write a possible equation because, as you'll see in later sections, there are a multitude of polynomials that are able to satisfy this particular solution set. But for our purposes, I know that my x-intercepts, so my x-intercepts, in this case, are going to be x is equal to -5, x is equal to 0, and x is equal to 2. So I have 3 x-intercepts. And we're going to try and actually reverse engineer what we're given here. Usually this is our result. This is our answer that we get from all our hard work. But here, this time, it's just given. So let's take a step back and let's think back to our other types of questions that we've used in order to solve for x, especially when we had quadratics or higher order polynomials. And what might come to mind is that, hey, when we're solving for x and we get multiple answers, usually what happens is we go from x minus some number is equal to 0, and what we get is x is equal to that number. So right now I'm doing a little bit of an abstract right here, but generally speaking, that when we are finding solutions, particularly x-intercepts when something is equal to 0, we usually set this up by setting up our parentheses and setting them equal to 0 and then solving for what value makes that parentheses equal 0 at that point. So we're going to use that fact and we're going to use that to now try and make our parentheses here. So we're going to create a parentheses in which x is equal to -5, in which x is equal to 0, and for which x is equal to 2. So what sort of parentheses would give me 0 when I plugged in -5? Well, the opposite of -5 is +5. So that means when x is -5, if I add 5, I would get 0. So using that logic, the way that I got -5 was from a parentheses, x plus 5 is equal to 0. Take a second, wrap your head around that, make sure that we put this into our notes in some fashion. But from -5, we get the parentheses x plus 5 equals 0. Now from our next intercept, we have x equals 0. Well, for this one, if we have a parentheses, something plus 0 is equal to 0, or excuse me, yeah, 0 plus something is equal to 0. Kind of gave it away there. But we know that the opposite of 0, well, is 0. 0 would cancel with 0, so this would be x plus 0 is equal to 0. And in this case, we have x something equals 0. And in this case, what would cancel with +2? Well, that would be -2. So there's a bit of a pattern going on. Whenever we have our parentheses, we always needed to solve for 0, which generally speaking switched our signs. If we had a positive value, we would get a negative answer. If we had a negative answer, we would have a positive value. So in this case, we're starting with the answer. I know that my solution was x equals to -5, which means I must have derived this from x plus 5 equals 0. I must have derived my 0 from x plus 0 equals 0. And I must have derived my 2 from x minus 2 equals 0. If that explanation is going over our heads, please do not worry about it. For right now, if we're able to recognize the pattern of what is expected of us, then that's going to suit us just fine for right now. So the rule is that whatever your solution is, whatever your x-intercept is, you're going to take that value, you're going to switch the sign, and you're going to make a parentheses that has x plus the opposite of what you're given here. So since we have a -5, what's in the parentheses is +5. 0 is unique because it has no opposite. So 0 and 0 are going to match. And when you have a positive 2 here, that means in your parentheses, you're going to have a -2. And joining those all together, our equation or our possible equation is going to be 0 is equal to, let's start the other way. We'll say x plus 5 times x plus 0 times x minus 2 is equal to 0. We're taking each of our parentheses and we're putting them all together because we're not trying to make 3 separate equations. We're trying to make one polynomial, one equation that we could use to get all these different solutions. And through some simplifying, we know x plus 0, this is just equal to x, meaning our simplified version of this is going to be x plus 5 times x minus 2 is equals 0. And generally speaking, if we have an x value, we throw that up front. So this is going to equal to x times x plus 5 times x minus 2 is equal to 0 is one proposed answer, one proposed equation to match this solution set. I just threw a lot at you guys. Please take a moment, go back, re-watch this section, re-watch certain parts, and see if we could follow along with with this particular question type before we move on to our next problem. All right, let's go ahead and see what the next slide has in store. Some brief annotation on here. Let's go ahead and just go over it. So it gives us the same information. The bold parts of each number line below show where the graph is above the x-axis. We're still working with that. And then we say the open circle shows the location of the x-intercept. And now we're supposed to do what we did for this example for our other number lines now. So I already set this up briefly where we have our x-intercepts labeled on our coordinate plane. So for our x-axis, -3, -1, and 4 are listed. -2, -1, 1 and 2 are listed. -1, 1, and 4 are listed. Take a moment to go ahead and try these examples on your own and compare them against what the sketch is going to look like. I'm going to pause briefly and see what it's supposed to look like. So now what we have is the sketches of what each of these is supposed to look like. These are not the only answers. If you want to be a little bit more bold and have it have a slightly higher slope or something to that effect, you can. But largely, this is what we're looking for as far as sketching these particular graphs. So we're given information about the intercepts and when we are above or below the x-axis, which gives us just enough information to give us a decent sketch of what's supposed to be happening. So please take a moment to pause and see if we're able to comprehend this, if what we wrote matches what this says. And if we're confident, then let's go ahead and go to the next portion where it goes into now investigating degrees. which means that we're going to be looking at our solution types and what that might imply about our function. So it says the degree of a polynomial comes from the highest power of the given variable. That means that if we have x plus 4, that's going to be degree 1. If we have x squared plus 4, that's going to be degree 2. The difference is in the power of our function. So it's related to the highest power, but the degree also reflects how many solutions the given function will have. So because we have a power 1 here, it's going to have one solution. Because we have a power 2 here, it's going to have two solutions. So using that information, we're going to go ahead and see what sort of trends we could notice on the number lines. So first, let's establish what degree polynomial do you think each of the following number lines represents? AKA, how many solutions do you think each polynomial has? Take a moment to take your best guess, your best assumption, and then we'll go over the answer momentarily. So the way that we count solutions is by counting where our x-intercepts are. We're basically treating the function as though we're equal to 0. And when this function is equal to 0, we have three outputs here. Excuse, three solutions here. So if I have my function set equal to 0, that answer I get back is -3, -1, and 4. When I plug in 0, I get three different solutions. When I do the same thing and ask the same question with my second example, I get an intersection. I get my line crosses through my x-axis at -2, -1, 1, and 2. And here I get x is equal to -1, 1, and 4. So, as we'll learn in later sections, this is not going to be definitive. It does not need to be these particular degrees. But our best assumption that we can do right now is saying that this first function is going to be a degree 3 function. This second function is going to be a degree 4 function. And this last one is going to be a degree 3 function as well. They're based off the different x-intercepts that we have, and those are indicators about how many solutions our problem is going to have. So using that information, so we had degree 3, degree 4, degree 3, and if we actually include our first example, we also have a degree 3 here. So sketching the graphs one more time. And we're actually going to skip over this third example for the moment, just because this is a unique situation. So we're not going to look at this uh, graph. We're not going to consider this graph for our purposes of answering this next question. We'll get to why in perhaps a later section. But suffice to say, it's not a good example for us starting out. So again, we'll just cross this one out for right now. But instead, what I want to include, actually, I'll ask that in a moment. But for this particular section, I want to ask, what degree polynomial do you think each of the following lines represents? How many solutions do you think the following has? I think it's, okay, so that's a duplicate, excuse that, which means, okay, then give me a moment to populate this slide. This is the slide that I want to be on. All right, sorry about that duplicate slide. But what I want to ask you next is, are there any similarities between the different degrees? So we have two degree 3s and we have one degree 4. Are there any similarities or difference that you notice between the degree and the kind of orientation we get the graph. Orientation just being the direction that the graph goes. Pause and take a moment and see if we could make any connections between what's going on. I'm actually going to throw in another example. So if we've already made some conclusion, let's see if that conclusion matches what I'm going to put here. But let's go back to our basic examples of x squared and x to the third. X squared gives us a parabola, and x to the third gives us, don't like that line, gives us this sort of shape. So did your conclusions about the different degrees hold up with these graphs where this is degree 2 and this is degree 3? If they did, feel free to keep going. If they didn't, then let's take a moment and just see if we can compare and contrast. Now that we have more examples. But what I wanted the conclusion to be is that when we have a all our 3 degree values started in one direction and ended in other direction. This was what happened with all our degree 3s. That we started in one direction and ended the other direction. We started down and then went up. I think that's true for all of them. Started down, ended up, started going down, we ended going up, started going down, and ended going up. And for our even powers, because degree 4 and degree 2 are not the same, but they have the commonality that they're both even, they start in one direction and they end in the same direction. Whether that's going positive or negative, they both go the same way. So that's one takeaway that we could take, that when we have an odd degree, we start and end in opposite directions, one positive, one negative. And even degrees, take it as they start and end going in the same direction. And we're going to use that information to further our understanding about what is going on as far as being able to sketch the graph, just being given limited information about the solutions. So with that revelation in mind, let's go ahead and take a look about what it's asking for next. So now we're going to go ahead and just take a pause and we're going to consider what we've learned and what information we should be bringing from other past lessons. So it says, consider what are the x-intercepts? Excuse me, let me take a step back. We're going to go ahead and go over the rules of what we know so far about how to interpret a function slash polynomial. And we're going to use that information to extract information about what the graph is going to look like. So first thing we should consider are what are the x-intercepts? What are the solutions for the function? And depending on what we have as far as our x-intercepts, that gives us the baseline of what our graph is going to look like. So depending on what our x-intercepts are, that tells us what points we go through. So the x-intercept gives us the foundation and telling us what points we go through. It basically sets up our graph, what our graph is going to look like. The degree tells us whether we're going to be beginning and end in opposite directions, or beginning and ending in the same direction. So that tells us that we should be paying attention to whether the degree is even or the degree is odd. If it's even, let's go ahead and actually space this out. If it's even, that means our graphs are going to end in the same direction, whether it's going to be positive or negative. Or if they're odd, we're going to be ending in different directions. So that means something like this or something like this. But we just know the beginning and ending of our line are not going to be the same. Speaking of positive or negative, orientation. Is my graph positive? Is my positive type of solution? Or is my graph negative? We could tell if a graph is positive or negative by its end behavior going to the right. We read graphs from left to right. So if our right-hand side of our graph is going down, that tells us that we're going in or we're dealing with a negative polynomial. If our end to the right is going up, we know that this is going to be a positive direction. Okay. If we're not entirely comfortable with that, that's fine. We're going to be doing more examples. But what I want us to do is be able to refer to these three questions and understand what information they give us about the function. And as we go through more and more examples, get more comfortable with setting up and sketching a graph using these three pieces of information. Okay. So if that's the case, let's go ahead and take a look at our next example. Because now we're not just given the x-intercept, but we're going to be told uh, we're given the function. So sketch the graph given the function. So instead of that being given the x-intercepts, we need to actually figure out what the x-intercepts are based off of this function. Thankfully, that's not too difficult because we are given this function in factored form. So I know that in order for me to get my x-intercepts, that happens when I get x minus 2, this parentheses, is equal to 0, and when x plus 5 is equal to 0. So doing some quick solving, I know that this happens when my x is 2, and I know this happens when my x is negative 5. So just by giving the function, I already know that my sketch is going to go through the points negative 5 and 2. So if I just set myself up like so, I already have the foundation of what my graph is going to look like. And now I need to look at the degree. So I have two x values, I have two solutions. So that means that this is going to be a degree 2, which means that it's even. So I know that my answers are going to go the same way. So from here, my two possibilities are something going like this or something going like this. Whatever I do, my function needs to end up going the same way at both ends. And then the orientation. This is back. This is going back and using some unit 2 information, but we could tell whether the function is positive or negative by looking at what value it has in front. If there's no value, it's implied that's positive. If there's a negative here, then the function is negative. Whatever value is up front indicates to us whether our function is positive or negative. So in this case, our function is going to be positive. So we're going to take the positive version of our graph, and I'm going to go ahead and sketch the graph. I know I'm going to start going up, and I know I'm going to end going up based on the fact that my function is both even and positive. I know that my graph is going to end up going up. So let's go ahead and graph this in red, actually. And this is all the information that the function tells you. In order to go deeper, you'd have to be given more information or, yeah, get more information from the given function. From here, we could pretty easily tell that that's going to be some parabola like this, just because we're familiar with this type. But you could also get creative as far as sketching the graph, because it very well could be a situation where you get something like this, or you get something like this, or you get something like that. Now, each of these is increasingly unlikely, especially for this given function. But what I want you to consider is that we're going to be being introduced to more and more complicated function types. So just take that consideration that it's not always going to be the most basic version of what we think the graph is going to be, because sometimes our functions are going to throw us for a loop. So, given this example, go ahead and take a moment and see if your sketch matches my sketch. Go ahead and take a pause and go ahead and try this one out. See if we're able to sketch the graph given this function. Well, this one is going to be a degree 3 function. Let's go ahead and get that off the bat. We know that this is going to be a positive function. So it's going to be a degree 3 positive function. And I know my x-intercepts are going to be -2, +2, and -3. Note, there's no reason to think that your parentheses are always going to be in order of your x values. So as you get information, please make sure that you put everything in the right order. Because if you just list it out, oh, this is even wrong. What did I put? Solve. So this should be x equals 2, x equals -2, and x equals 3. Never skip the solve step. So this is going to be -2. Even more so, our middle number is actually what starts us out. So please make sure whatever your x-intercepts are, that you list that out in order on the actual x-axis. So that's going to be 2. That's going to be 3. Okay? And based on my degree and based on my positive value, I know that my graph is going to end in a positive direction over here. And because it's a odd degree, that means that it's going to start in an opposite direction, going down. From there, I have some liberties to take, but I know it's going to go through here, here, and here. This is the most basic version of our answer and what I expect your answers to look like more often than not. But it also could be something like this, as we saw in example number 1. Doesn't not always need to be the transition between above and below, but it very likely is. So we're going to go ahead and just keep this as our final answer as far as sketching the graph, given the information that we have from function. Okay. So we have one more example that I'd like to go over just because this one is negative. But once again, I want you to go ahead and try your hand and see if your result matches what I'm about to do. So please pause the video, see what you can do. So like the last example, this is going to be a degree 3 because I have 3 different solutions. And because of this negative in front, this is going to be our first negative example. And of course, I must solve to get my x-intercepts. That's going to be x equals -6, x equals -3, and x equals -2. Lots of negatives in this one. So I'm actually going to start my line more over here. So I can make room -6, -3, -2. And because it's going to be a negative degree 3, I know that my end is going to be down here. And because it's degree 3, I know that my ends start in opposite directions. So since I know that my function is going to trend downward because it's negative. Because it's degree 3, I know that it starts the opposite direction. And because of that, we're actually going to sketch something like so. And this is the sketch of my graph for this particular function. Again, that's not the only way of doing it, but what I would recommend is that you keep your variations to just being exaggerated how high or low it goes. So it could be something like, oh, it only dips a little and it dips super high over here. But suffice to say that we want to keep it generally alternating between our x-intercepts, whether the line is above or below the x-axis. But with that in mind, we just have 3 more examples that I want you guys to try on your own. Make sure this makes sense. Go back to the video if we're not sure how to continue or proceed with any one of these problems. And if we have time, then I would like you to consider the next part of this section, which is if you're given x-intercepts, but now you're passing through a particular point, how can I take this information and write a function? So now I'm not just worried about the graph, but how would I take this information and now write a function that satisfies this information, that would satisfy a graph that goes through all these points? But with that being said, happy studying, and I hope that we're able to hit the ground running next time. Take care.